So we have that here, right? So isotopes themselves, unstable isotopes, would actually produce these different types of particles when we eject them, right? So here, the alpha particle, right? The alpha nuclei, the alpha decay would give us a helium nuclei, right? What the alpha particle really is two protons and two neutrons, right? And because it's two protons and two neutrons, it's the same as the helium nuclei, right? So because the relative mass of proton is 1 and the relative mass of a neutron is 2, if we have two protons and two neutrons, the mass number would be 4 and the proton number would be 2. Right, so if we were to decay something like fluorine, as we were stating before, right, we're going to take away 4 from its mass number, right, and we're going to take away 2 from its proton number, its atomic number. And what it would be the answer? The alpha decay of fluorine would give us what?
Three for mass number and 7 for the atomic number.
So it would give us. Alright, hold on. What is the mass number of fluorine? What's the mass of fluorine?
Mass number is 19.
19.
Atomic number is 9.
So fluorine 19, right? So the mass number is 18.998, right? So generally we can call it 19. So if we're just going to call it 19, right? So it's 19 minus 4, which is 15, right? And then if it's
15.
atomic number itself, we know that atomic number is 9. So if we take away 2 from 9, we get
7.
7, lovely. And the atomic number, the element responding to 7 would be.
Carbon. Nitrogen.
Yeah, nitrogen.
Somebody showed carbon with their entire chest a while ago. Alright, so nitrogen is atomic number 7 here, that we can see there. Right, so here, right, it would be our nitrogen 15, right? And then now we will actually add our helium nuclei. Right? That would be it, showing the alpha decay of fluorine. Right? Alpha particles are generally weak and stopped by a thin sheet of paper. Beta decay, no. Right, what we're looking at is the loss of a general electron. Right? We tend to really look at something like that. So what would the beta decay of fluorine look like? So it's not really the loss of an electron, right? It's the loss of a beta particle. I want to look at how beta decay really looks. How does that look? What's happening for a beta decay?
You're gonna get.
Repeat.
You're gonna get in same 19 as the mass number, but the atomic number can change to 8, and you're gonna get the electron coming out.
All right. So what tends to happen in beta decay, right, is that something is changed to something. And as you stated, right, one of the neutrons is said changed to a proton. Is that what you stated?
No, I just said the atomic number then lose a proton.
The
I
atomic.
didn't set up a this, like yeah, the atomic number can change from 9 to 8.
All right. Okay, so if we have something like that, we're gonna have the atomic number changing from 9 to 10, right? So we're gonna have a general increase there in the atomic number, right, from 9 to 10. So fluorine will become neon, right? And fluorine, let's for example, if we have fluorine 19, right? It's going to give us neon 19. Right? So what we're basically doing is increasing the atomic number there. Right? So it basically involves a proton in the nucleus converting itself to a neutron, right? So it's something like that. That would be our beta plus decay, right? That we have, right? So we either have that beta plus decay there, right? Or we have a beta minus decay, right? So beta minus decay would actually have us increasing, right? Our mass number by one, right? And actually increasing our atomic number by one. And our beta plus decay would actually be the opposite, where we're going to decrease our mass number by one and decrease our proton number by one. Right? What beta decay is really the transformation. I'm trying to find a simple way of explaining it. It's really just a transformation of some particles, right? And the release of a beta particle, right? So an electron, right, itself would be released in a, for example, right? And another fundamental particle, but we generally just show it here, right? It's what we call I'm not sure if I should mention the name of the particle because I'm not sure how far I should go with this, right? But we have that there, right? So what we tend to look at in beta decay is the transformation of a neutron into a proton, right? And we generally have it increasing from fluorine to what neon would be, right? So if we have something like this, we're gonna end up with fluorine. We're not gonna end up with fluorine changing to neon. All right. So we have that. I have a question though. Really, really important question. With beta decay that you guys look at, right? I want to know which beta decay you actually look at. Is that the same beta decay you look at the increase in the atomic number by one? Go ahead.
I was asking to repeat.
What type of beta decay? The beta decay that you guys look at would be increasing atomic number by one, yes?
Yes, sir.
Yes, sir.
Alright, and the mass number doesn't change?
No, sir.
Doesn't change.
Uh,
Alright, so that's what we're having here, right? We're increasing the atomic number by one, and let's leave the mass in there. Because I think at this level we just speak about that change, right? Okay. Because I was about to talk about the antineutrino and the positron, right? But this is what we're having here, okay? So the mass number increased by one, sorry, the atomic number increased by one, mass number remains the same. For the alpha decay, right, we're going to have, we know our atomic number decreasing by two and our mass number decreasing by two, right? So what I generally use to remember this, right, normally just write the alpha sign, right, and I have a down arrow, right? I have my alpha, right, increasing by, well, decreasing by 2, and my mass number decreasing by 4. For my beta, right, I'm going to have an increase in my atomic number by 1, right, and then nothing for the mass because we don't touch the mass, right? As it relates to gamma, no. Gamma particles, no. Gamma decay itself is just a release of high frequencies, right? And those can be stopped by a thick lead sheet. Those are the most penetrating of the emissions, right? So alpha is the least penetrating, then beta, then gamma, right? So gamma decay, I don't think we actually look at questions asking you to actually show an equation of gamma decay, right? Because generally it's just release of energy, right, from the atom itself. You won't really have the atom changing into something else per se, right? At least not at this level, right? So generally looking at beta and alpha decay, those are things that they can bring on the exam. Questions, concerns?
So in the textbook, they show that with the gamma decay, the
Mm-hmm.
the it is like the opposite of the beta decay. So
Opposite of the beta decay.
yeah, so the atomic number decreases by 1 with the
Alright,
gamma.
so they actually show you something. Alright. So we have that there. see me not doing keeping a while. It's me trying to, because I'm trying to feel out where, where should I go in depth, where should I not go in depth. Alright, especially as it relates to topics as simple as these, right? So we have alpha decay here, beta decay, and gamma decay. Alright, so in your gamma decay, it actually shows that what is being released as a high energy would be, well, at high energy would be similar to a proton, and that is what is going to be released at a high frequency, right, in the electromagnetic spectrum. So it's like a high energy photon, something like that, that is released, and that would be generally one of the positive charges from our nuclei, and what we're going to end up with is something that decreased by 1, right, our atomic number by 1. So if you have the gamma decay of fluorine, it should decrease the fluorine to what exactly? What would fluorine change to? If it decreases the atomic number by 1, fluorine should change to oxygen. Alright? So it's really just the decay of these molecules. So if we have something that is truly radioactive, right, something like a uranium, right, if uranium will go through gamma decay, right, then that would just decrease its atomic number by 1, giving it the same configuration of protactinium here, right, just atomic configuration I'm speaking about, right. If we were supposed to have the beta decay of uranium, we're increasing the atomic number by 1, which will give us neptunium, right? And if we were to have the alpha decay of uranium here, right, that should give us around thorium, right? But obviously we're gonna have the mass number decreasing, right, by around 4, while the atomic number decreases by 2. All right, so it's really something like that. That's really how the questions can really be posed. They can ask you to give a element A and allow element A to go through beta decay, then alpha decay. They can ask you a series of questions like that, right? And examples of how alpha and gamma decay, right, happens is given here, right? Alpha, beta, and gamma decay is given here, right? So the band of stability, right? So this is something that we tend to use to figure out whether or not something is stable. Go ahead. I think somebody raised their hand or something. Or
Sir, I have a question.
Mhm. Go ahead.
It had a past paper question that asked which of the following types of radiation would most likely be measured using a Geiger counter. You know which one?
A Geiger counter. What does a Geiger counter measure?
I'm not sure.
So that is where we need to start. We need to know what the Geiger counter is. Alright. So need to know what that is first. Alright. I want you to show the past paper question when we reach there, right? So we want to go through those questions. For use of radioisotopes, these are generally things that you guys need to know, right? So we would have looked at some of them in fourth form chemistry. So a lot of our radioisotopes are used as tracers. So if we look at something like a deuterium, deuterium is used in chemical analysis. Tritium is used, right, as a tracer, right? Iodine 131 is used for some amount of tracing as relates to thyroid function, usually used to mark those organs, right? In medicine, radiotherapy, right, in the treatment of cancers. So if we look at something like radium, using for x-rays and stuff like that, that is important, right? Carbon dating for carbon 14, smoke detectors for americium 241, and generating of nuclear power, right, by uranium 235. These are things that you guys should generally be able to come up with. If they ask you to state the use of generally 3 radioisotopes, you guys should be able to do that. Shouldn't be much of an issue, should it? Don't think it should. And then here's just a list of questions that you guys should be able to do. And this list of questions looks very familiar, and that is because it comes out of a textbook. Alright, so you guys should be able to answer these. Shouldn't be much of a problem at all.